Yes, one of the tricky things is then you want to choose, then you want to know what features are the most interesting ones to use, right? Maybe color isn't that important. This is kind of gets into feature selection. It's kind of, that's kind of like, okay. So we'll talk about a little bit of that regression section of class, but there won't be any answers. But you can start thinking about those things. Basically what you want to is some subset of features that is as small as possible, but still give you a great answer. So that also good maybe we'll talk about some methods to do that towards the end of the section of the regression class.
Maybe if we show you the stamp here.
It's a Google Doc, we don't know how to not.
Yeah. Yeah. Okay. Yeah, you'll get some sort of penalty, but yeah, but still submit that the way you would normally. And also send me yeah. Okay.
Yeah, assignment. There's a bunch of notation that's expressing what has these. It looks like it's the absolute value, but it has a subscript.
Yeah. Okay. So there's 2 bars next to each other. 2 bars. This means the norm. Two norms is you set on the side of the board. So if there's 1 bar that's either an absolute value and 2 bars.
Do you want me to draw where you're at today?
Yeah. Typically, it's done like subscript.
If it's some or some C1 minus C2, it's saying like C1 minus C2.
Right, so those are both vectors.
You just need those vectors. It's translating this between the vectors is all of them. The subtraction is
Actually returns the vector.
Yeah, especially because this project's like new.
The length of that vector is
Yeah, so it was like super earlier on. Like we did like just have like that.
So subtract the vectors and
I submitted it.
Yeah, no, we built that.
So if you draw a picture,
I think I get it.
and that vector you can translate to the origin, but this length of it doesn't. Right, so. Okay.
I'll ask my question on the board. Yes. So basically, you just pick like a start, and you say, so starting out, they all technically be assigned to this question.
Correct.
And then you say you take this point that's farthest. But is that point farthest from this point, or
That.
this one?
Yeah. That's right.
And we're saying Kate risks only like 3 minutes?
Correct. Yeah, it's likewise.
Yeah. Okay, so the assigned points don't factor into like the mean of the.
We're not doing the mean in this one. The point is that this one works even if you can't take a mean. If you're using Jacquard distance, you don't have to take a mean. You still run stuff here.
So we figured out.
Hey, so let's get started. Let's see. Okay, so we're going to talk today again about streaming algorithms. So again, it's going to be we're going to talk about variations on frequent items again, but we're going to change it in a few ways. So again, we're going to talk about frequent item. That's kind of a weird way of writing it, but frequent items and frequent item sets as well. But also, if we have time, we'll talk about just finding collisions with Bloom filter as well. So we're going to talk about kind of three things: the min, count, sketch. Can't spell today. All right, here we go. I can't possibly do it. Okay. Okay. So sorry, I woke up this morning. I woke up in a different state, so I'm a little out of sorts. It was intentional, don't worry. It wasn't like I was in Wendover this morning or something like that. Has it happened to anyone? Were they like, oh no, I'm in Wendover? Okay. Even if you're intentionally just driving to San Francisco and you realize you're in Wendover, it's kind of a little bit frightening. All right. Okay, so sorry, the first thing I was talking about was the count min sketch. This is going to solve actually the same, more or less the same problem we talked about on Monday, the frequent items problem. But it's going to use a completely different approach and have slight and various other advantages on top of the Misha-Gries algorithm. And there's a very similar algorithm called the count sketch, which I'll also talk about. And this will be much more similar to the count min sketch. You can tell by just looking at the names. But we'll also have a little bit different properties. Then we'll talk about these a priori, what's known as the a priori algorithm. And this is kind of like in classical machine learning. If you took a machine learning class 10 years ago, this would have probably been something you spent maybe a few weeks ago. There's still machine learning, data mining. Classical data mining, if you took it 10 years ago, even 5 years ago, you may have spent a few weeks on this topic. There's still some classes taught around the country that still spend a lot of time on it. I'm going to spend half a lecture on it. I don't know, just personal preference, but some people find it very useful, so it's just something I mentioned. This is the for frequent item sets. So hence how I got that weird looking title. This is a parentheses, right? So frequent items and sets. Okay, so this is seems like a very useful problem. The usefulness, there are kind of other approaches which kind of come to tackle this from a more statistical perspective that happen later on. And it's kind of related to this frequent items, but is different in some ways, and it's kind of from a theme. How the algorithm works is also a bit different. And then, if we have time in the lecture today, you'll see there's quite a few things on this list. I'll mention Bloom filters, which are going to be very similar to the structures, the count min and the count sketch we'll talk about earlier, just to kind of put this in perspective. So, because people, usually some people ask me, how does this relate to Bloom filters? So, has anyone heard of Bloom filters? Okay, Yeah. So the count min sketch is going to look kind of like a Bloom filter, and so people say, is that a Bloom filter? It's not a Bloom filter, but it shares a lot of similarities. So I'll describe this and the differences at the end, given I have time, or you can. Okay, so hopefully we'll get to that. All right, and the notes that I wrote on here, I usually save on the web page. The Surface crashed and didn't save them last time, so they're lost and gone forever. Hopefully the LaTeX notes I have up there are already have enough information, but sorry about that. Okay, so let's review the streaming setting again. So for streaming, you have a data set A, and you're going to be presented this in some order, up to usually some AI, and we'll write the last element as A N. I think that's, no, we're using M. Okay. M is, so there are M elements in the stream, but at any given time, we've only seen up to some point AI. So this, sometimes we'll call this set a big AI. It's all the stream up to this point. And we're processing this. We see this one item where we get to do something fast with our CPU, and we have a memory which is of limited size. So we're trying to keep some statistics on this with using a small amount of memory. And so then for the frequent items problem, we're assuming that each of these AIs comes from some universe of bounded size n, right? And so then the frequency fj of the jth element in this set, so j is in the set n, is we look at the set that we've seen so far, all the AIs, such that AI is equal to j, and then the size of this set. So this means such that it's slightly shorter than the ones on the outside. This is, if you see it in the LaTeX document too, this is the notation used. And so these are all the elements that are the jth items. So these are, think of IP addresses. This is the IP address of your computer that's some secret agency might be monitoring. If you're sending a lot of suspicious messages, then they want to know about it. Right? So we want to find these frequencies that are high. So some IP address which occurs very frequently. And so we're going to get some sort of guarantees, and I'm going to write this slightly differently today, because this will fit what the algorithm is going to do. It's going to have the property we want to come up with this fj hat for all values of j. And how we deal with the all values is going to be different today than Monday. Last time we limited space. How do we solve all values? Well, the ones we don't report are implicitly 0. We're going to do this a different trick in this class. And so it's going to be where in this time they're going to be greater than the true value, but not too much greater. Okay? So it's always going to be larger than the true value, our estimated value, but not larger by too much. Before, it was smaller than the true value, but not smaller by too much. And so you can also estimate whatever this quantity is, and you can add or subtract that from your estimates. So these are, you can get either one of these bounds. Okay, and okay, so this is the goal today, is to provide these estimates. What we're going to do today is we're going to explicitly construct a data structure, S of A. And so then we can ask, or let me write it, say data structure. So this will be a data structure. So think of this as you're creating a data structure, you can insert stuff into it, and you can ask certain type of queries. You have an API for your data structure. And you're going to ask some value j, and it's going to return to you fj hat. So you're only going to have access to this data structure this time. You're not going to kind of have these counters in the same way that we had before. You're just going to be able to ask queries to this. Okay, so, and this data structure is going to be random, so it's going to turn out that this bound is going to be always true. This is going to be true with probability at least 1 minus delta for some other delta parameter that's going to go into the size. So we want this to be true with really high probability, and so this will be something we can get. So it will always be larger. We'll never underestimate, and we won't be too much larger with some probability. It could be that we got unlucky and things were much larger than our worst case scenario, but in general, it'll be okay. All right, and so the trick we're going to focus on today that's going to make this work, which we did not use on Monday, is going to be hashing. Right, so our old friend hashing from the first kind of, we talked about a lot earlier in the course. And so, again, just to remember, a hash function is going to be, is a deterministic function from, in this case, it's going to go from n to a smaller set k. Okay, and this is going to be hash 8, or in this case, let me use a different symbol. We'll do this, I used h in my notes, so it was h of lowercase h. Let's use an r here. Okay, so r is going to be random. So hr is going to be drawn from a distribution of hash functions. So when we pick this, remember when we pick this hash function from this distribution, now it's deterministic, but this choice was random. So like if you used a built-in hash function, you used a random salt or a random seed to it, and you, as long as you use the same random seed, you got the same result every time, right? So this is, remember how hash functions work. And so in this case, again, we're going to pick some number of hash functions. I use index r because we're going to have r go from equals from the set 1 to up to some variable t. So we're going to do t of these hash functions. Okay. All right. And so, okay, so now this is kind of the ingredients we need, and we've seen all this before. So, and again, we're just going to use, so we're going to use hash functions and counters, but we're not going to need labels. Okay, so let's go into the count min sketch now. So the count min sketch. Okay. So instead of keeping just a set of k counters, we're going to keep a table of counters. Draw this well. So we'll do, this will be C, counter 1, 1, we'll have counter 1, 2, counter 1, 3, up to counter 1, T. And it's going to be longer this way, so this will be counter 2, 1, counter 3, 1, to counter K1, and so forth. And this will be counter KT. Okay, so we have this table of all of these counters, and so to initialize Cij is going to be equal to 0. So we're going to start with all the counters equal to 0. Okay, and so I said we had T hash functions, so I'm going to put H1, H2, H3, up to HT here. So each row is going to correspond to a hash function. Okay, and this is the setup of the data structure. Okay, so now that I've told you, instead of having kind of k counters and labels, now I have k times t of these counters and t hash functions. So now what should I, and my hash functions, sort of view my hash functions go from 1 to k. So I can get an item in, and it tells me it goes to one of these hash functions, right? So I have c, I, j sits here something. So let's make this 3j. Okay, so now, how would I do this? What should I, how should my algorithm run? Any ideas? So, you know, there aren't too many options here. So, and again, there are going to be two right answers. The count min sketch and the count sketch are going to use the same, roughly the same structure here. So what would you do with an incoming point, right? So remember, the algorithm for the count min sketch is going to go for AI in A, right? So I'm going to loop over all these elements, or I've written it for I equals, this is RJ. For I equals 1 to M, right? So I loop over all the elements in my stream. Okay, and so then, what should I do with each AI, each element of the stream?
Hash.
I hash it. Good. Which hash function should I use?
Maybe all.
Use all of them. Good. Right. So if I take an element, if I have an element AI that comes in here, I'm going to push it into the hash function h1. So h1 of AI is going to map to some value. We'll call this R, which is going to be in this, go from, well, I guess this was J, to a value J that goes from 1 to K. Okay, so that means it's going to go, let's say it went to 3. Let's say h1 went to 3. I'm going to go to this counter, and h2 will go to h3. So this will go here. h3 maybe will go out to the ith thing, or the out to the jth thing, right? Right. So in each of them is going to go to a different. Right, to a different one of these counters in this set. Okay, good, good. So the first thing I do is I'm going to hash it to one of these counters, and then I should. What should I do with the counters once I found them? Increment them. Good. So I'm going to increment the counters. All right. So let's try and write this down in the algorithm. So then for R equals 1 to T. So iterate over my hash functions. Try and write this down. So counter the jth. So this is the jth row. And then the counter I hash to is the hash of J of AI. So this tells me what counter to find in here. Right? So I've hashed to the jth counter. Which one did I hash to? H of, this is the R one. Okay. So C of R, H of R. Okay, so R is 3 here. The third hash to the jth counter. J is this quantity here. All right, so this quantity is J. So I've hashed to this counter. I'm just going to increment this counter. That's it. So for each, every time something comes in, for each of the hash functions, I find the counter associated with it and I increment it. That's the whole, it's the whole data structure. Okay? I don't have to worry about if I run out of counters. I don't have these if conditions. I just increment these counters that I've hashed. Yeah.
How do you determine how many hash functions?
Yeah, so it's going to depend on how accurate you want it, right? So these parameters and all. It turns out what you'll want to do is you're going to set k equals to 2 over epsilon, and t is going to be log of 1 over delta. Okay, and this is log-based 2. And so typically this is like between 5 and 10. It's going to be enough to have a really low probability of failure. If I set this to be like 5 or 10, it means that delta is going to be very, very small. This grows. If delta grows small, this really quickly gets or this grows very small as a function of 1 over delta, right? So if delta is say 1 out of 1,000, right? So I fail 1 out of 1,000 times, right? So then it's log base 2 of 1,000. 1024, log base 2 of 1024 is going to be 10. So if I fail roughly 1 out of 1,000 times, that means the whole data structure is correct. This is what it's going to turn out to be. 1 out of 1,000 times. On doing this, I need 10 rows. So think 5 or 10. And then k is going to determine my error. This is going to end up being the right error parameter. And we'll see why this is in a second. Okay. So you set the number of rows, and so this you may want to be like 200 or something like that to get 1% error. Okay, so good. So this is the whole data structure. This is how you do the updates. I still haven't told you how to do the query, right? So this is the this is how I do the update. How do I do a query, right? And by query, I mean if I have my data structure S of A and I ask for J, right? So I ask for the value J. How do I get, this is supposed to be this F hat J. How do I return this?
Maybe something like average the counters for each row.
Yeah, good. So I want to look at all the counters, right? So I want to, how do I know which counters to use?
Use one that hashes in.
Right, so if I hash J, if I hash the value J, it tells me what are the right counters. Precisely, these hash functions are deterministic once I've chosen them. So every time I saw something with the value J, I know exactly which counters I incremented. So those are the counters that I want to look at. So I want to do something for over all the counters R hash of R J, right? So for each value of R, what went from 1 to T, this tells me the right counter. So I can index into those right counters, and then I somehow need to average them or something, right? Is average the right thing?
Minimize.
What?
Where should you find the minimum?
The minimum, good. Right from the title of the sketch, right? Yes, it turns out you actually want to find the minimum. So why is the minimum a good idea?
Because different values were hashed into same box.
right? So you said different values hash into the same counter.
Yes, and counter, so the so the minima is more likely it's the only one. I don't know. Just the-
Yeah. Okay, you're getting close. You're getting close. The minimum is good. Why is so? Yeah.
The item you're looking for is always going to go to the same bin.
Right.
So the smallest one will be, every time you've seen that item, it will have incremented that counter.
Okay. Good.
And so whatever that minimum number is you at least are at most in that many times.
Right. So here's maybe a different way of looking at it. Is it possible to return a value to see a counter that is smaller than my true value? No. Right? Good. I can't ever underestimate in any of the counters. None of the counters will underestimate it. So they're all some form of estimate, and they're all larger than the true value. So I might as well take the smallest one. Right? So the smallest one is going to be the one that must be closest because they're all larger. Because every time I saw J, or every time I saw my query J, I used J twice here. Okay, so let's change this in notation, otherwise. To query. So every time I saw Q, every time I saw query Q, it's going to go and increment this. Now I might get error. I might, because could be hash collisions, there probably will, then some other things might hash at the same location and also increment it, but they're never going to decrease the value. They only increment. So I get error when there are collisions, so I can only get something larger. So my best thing to do is to take the smallest possible value. Okay? So if I take the minimum, I already know is going to be less than the value I'm returning. Right? So it's going to be an overestimate. And so if I take the minimum over a bunch of overestimates, this is going to be my best thing. Right? So now the question is, how much of an overestimate is this going to be? Right? And this is going to go into why we chose these values of K and T. Okay? Right. Okay. So this is going to be less than the true value f of q plus some w. And so now how large is this w? All right. Okay. Is the algorithm and how you query it clear? It should be it's a fairly simple algorithm, very simple algorithm to implement, very simple to use, right? Why it turns out is also not too complicated, right? So let's go through this. We have to use some now randomized analysis. Okay, so let's so we're going to describe a random variable. We'll call this YRQ. Okay, so this is going to be for the rth row. So this is the rth which hash function. And so the Q is going to be a specific query. Okay, so for this random variable, this is going to be defined as the amount of the overcount. So technically, it's going to be CR of HRQ minus the true frequency of Q. Right? So how much extra stuff is going to be in this counter? and actually it'll be simpler to actually analyze just this. So we'll ignore the effect of this variable itself. We'll just analyze this counter. If you can add this back in and it gets a slightly better balance, but so now again we're going to use that. Let's see. So y of our q. Oh, let's change this to actually, sorry, I want to change this to actually use j here. So I'm going to look at the j. Well, okay, let's actually ignore this part. So the amount of stuff. So it's going to include all the counts in here. So this is, but this is just going to be the effect of all elements with. So this is in n. So I'm going to say the amount of the amount of counts from Q in n. So of the objects we see that have a value Q that go into this counter. Okay? So if they go into this counter, we're going to see that it's either going to be the value f of Q with probability 1 over k or 0. Okay, so if you look at all the elements that have value Q, these are going to hash. Sorry, I'm getting. So this is going to be, yeah, so good. This is J, but this Q is based on, so the query, I'm looking at the query that I care about. So the particular counter that is affected by my query on the row R. And this is the Jth element, which let's say is different than Q. So this is set minus Q. So one of the elements J that's not Q, that hashed into this counter. Okay, so it's going to either have an effect of f of J here. It's either going to have an effect of f of J with probably 1 over k if it has a collision, or 0 if it does not collide. Okay, so that means that the expected value of Q is going to be f of J over k. So for any other value other than Q, for any other address I see other than my own IP address, the expected effect on my counter is going to be the total number of times this IP address occurs divided by k, because that's the probability it collides. Okay, so now if I look at the sum over J in n, right? So from J from 1 to n, say set minus Q of these, the expected value of YRJ. So the expected influence of all of these other values by the linearity of expectations is going to be QRJ equals sum over J of f of J over K. And this is exactly going to be M over K. Right? So if I ignore, so the sum over all of these terms, all of these counts of everything, is the total number of counts I've seen. Now if if I'm being a little bit more careful, I can subtract out f of q. Right, but this part is the part that I don't really need for my the ultimate bound limit. Yeah.
Would, trying to understand this, would having a greater number of distinct elements in your M have any difference?
Turns out it's not going to have any difference for this one. For the count sketch, something like that is going to make a bigger difference. It's just that the total sum of them all. This one is not affected by the variance caused by this distribution. It's just easy to see that each thing is correlated, and its effect is essentially random on the probability of it falling in this bin is 1 over k for each other item. Okay, so the expected effect, the expected overcount of all the other counters. So now I can say something like what this is saying in Word is the expected overcount in row R is going to be m over k, which, if we remember, by setting k equals 2 over epsilon, this is going to be epsilon m over 2. And so the expected overcount is epsilon m over 2. So this is good. This is less than what we said was this overcount which occurred with very small probability. So we're on a good chart here. Yeah.
So this is basically saying that all the items that aren't Q are going to be evenly distributed across all the other bins. And so most you can get in the bin that we're interested in is
The expected number we get. Yeah, so if they were totally evenly distributed, we can do a slightly tighter analysis on this, actually. But because they're kind of clumped together, you could have some very heavy items. One item, if it has the wrong collision, could put us over our threshold. So otherwise we could use a Chernoff bound to bound this. It turns out that there's going to be a weaker bound we can use. There's this Markov inequality, which we're going to say the Markov inequality says that the probability that absolute value of some random variable alpha, of some random variable x is greater than alpha is less than the expected value of the absolute value of x. Actually, it shouldn't be. You should actually just enforce if we know that x is always greater than 0. So it turns out that this overcount is always greater than 0. And so the probability that it's greater than alpha is less than the expected value over alpha. Okay. So this you can say if it's always greater than 0, its expected value must be greater than 0, and if too much of it is very far away, then the expected value couldn't be so big. So if you've never seen this before, you can kind of think about that statement a little bit and kind of rederive it. But if we're just using this, what we're going to do is we're going to set this now. What we want this to be is to be epsilon m. Right? We want to say that the probability, we want this to be 1/2, and we want alpha, write this in another color here. So we're going to set this to be 1/2 by setting alpha to be epsilon m. And this works out because the expected value was epsilon m over 2, and this was divided by alpha, which was epsilon m, and that's going to equal our 1/2. Right, so we say the probability is greater some random variable, which it turns out is the sum of all these counts. Right, that random variable right here. This was our random variable x. So we say the probability that the sum of all those overcounts is greater than epsilon m is less than the expected value, which was epsilon m over 2, divided by epsilon m, we get 1/2. Okay, so what this says is the probability that any one of the rows is greater than epsilon m is at most 1/2. Okay, so we have t of these rows, and each of the rows was independent. So now we can say the probability that all of them were greater than epsilon m. So the min of the rows of all these, you know, so that the r min of r in t of the sum over j of y rj is going to be greater than epsilon m, right? So now, if the minimum, meaning all of them, are greater than epsilon m, this is going to be, because they're independent, this is going to be less than 1/2 to the power t. And remember, t was equals to log base 2 of 1 over delta, right? So this is going to be equal to 1/2 to the log base 2 1 over delta, which is going to be equal to delta. Right? So now the probability that we're too big, probability that we've too much air, is going to be at most delta, which is what we wanted. Okay? So we just proved the correctness of this randomized algorithm. Typically, you just like we did, you set up your random variables correctly, you apply some tail-bound, in this case the Markov inequality. We talked about the Chernoff-Hofting inequality, which is more powerful before, and then you plug this in and you get some bound numbers. So does this kind of make sense? You believe this works? So each of the estimations, overestimates, is spread out. So the expected value is pretty good, is small about the error. So if you do it a bunch of times over and over again, then the minimum of them shouldn't be too big. Okay, so this is the Countman sketch and how it works. Very simple to use. Okay, so how much space did we use for this thing? So what is the space for the Countman sketch? So how many counters? The number of counters was equal to k times t, which is equal to 2 over epsilon times log 1 over delta. And each of these counters had space log m. But we didn't need any labels, so how did we avoid using labels? Yeah, the hash functions. Turns out a hash function costs about as much as a label. So we had t equals log 1 over delta of these hash functions. So this is the space of one of the hash functions. Okay, so how does this compare to the Misha-Gries sketch? It's more or less than the Misha-Gries sketch. The MG sketch, it used 1 over epsilon times log n plus log m. So probably log n and log m are probably about the same. They're probably going to use like a single integer or whatever for both of these. Right? So then, you know, it's going to be roughly the same size. I have a 2 over epsilon. I've got this log 1 over delta factor, which is about 5 or 10 now. So I'm probably increasing the space by about a factor of 5 or 10. So this one about log 1 over delta 5 to 10 times bigger. So it's bigger. So why would I want to use the count min sketch? There's something cool I can do with it. What happens? So one thing I can do, and this is probably not obvious at all from what we've talked about. So the count min sketch can do subtraction. So you can subtract something out. You can remove an item that you put in before. So let's say I accidentally, I had a typo into my sketch. Can I go back and fix it? I can't with the Michigrees. Once I've done this this thing where I subtract something from every counter, you know, I don't necessarily know what I had anymore. I can't go back and fix that. But with the count min sketch, it's easy to go back and fix. I just go to all my hash functions, and in update, I just do I do a decrement instead of an increment. Or minus minus on subtraction. So I can decrement these counters if I'm doing subtraction. And as long as I don't take out more than I put in, then everything works fine.
The what conditions would you subtract on? I didn't catch that.
So like if you're putting in a bunch of documents, and you said, no, I don't want to include this document in my data set anymore. I'm going to take this out. Or you could say something like, this is often called the, so in subtraction, it's often called the turnstile model. So you're at like a football stadium. People walk through the turnstile when they go in, and then they come out. So if you're keeping track of things passing in or out of a set, then whenever something leaves, you want to subtract it. So I'm getting error based on only the things left over. So I could think of, what would you use this as? So say you're sending some messages back and forth, or you're trying to reply to all of your emails, and you have a bunch of emails coming in, and when you hit a reply, it removes something from the set, right? So I don't have. So how many emails have I not replied to yet, right?
Well, that's
so
the model for these streaming algorithms. You only had access to the data at the time that you initially saw.
yeah. So think you have another part in your data set that tells you, here's an item, you're removing this from the set. So I only see I have some firewall set up, and it sees emails coming in, or from some IP address coming in and going out to an IP address, right? So if I know that I have more coming in than I have going out, these are the things that I still have in my set, then I can keep track of this. It comes up in some various things. So one thing you might want to do, and to do this is a bit more, to get this to work, it requires some extra layers of stuff I'm not going to get into, but you can think of this as your stream, and you want to look at, so typically we've been saying we're interested in this data set going back to the beginning, but there's a notion of what's called a sliding window, where if you change it to go here, then you shift it forward a little bit. So you always keep it of a certain size. So I want to know what happened over the last day. So there's some way to keep track of this information internally, and then you remove it from a sketch at some point. And being able to subtract. So you need to keep some more detailed stuff inside of here to get this to work, but being able to subtract out of a sketch becomes useful. There are ways to do it without subtraction, but this helps. It could be that you're saying, I'm keeping track of, say, there are things where you actually get an update, like otherwise this could be a subtraction event. Otherwise, and so otherwise you could see this subtraction and then you go and you note decrement instead of increment.
So that means you'd see every data point twice?
Up to twice. Up to twice. You can't subtract more than you add in this setting. There are other techniques to do that. They usually get, the error bounds get more complicated to state, because then you don't have a total number of things you have to talk. You can sometimes do it with absolute values, but it gets messier. Okay. How are we doing? All right, so let me spend 10 minutes just talking about the count sketch. All right, so the counts. So historically, the count sketch was invented a few years before the count min sketch, but it's a bit more complicated. So again, you have the same setup as you did before, C1, 1, C2, 1, up to CK1, C1, 2, up to C1T, CKT. So you have all these counters. You also have these hash functions. And you're going to also have a second hash function, which is going to be simpler. And so now this is going to be a sign hash function, S of R. And this is going to go from your set and again, but just to a -1 or a +1. Okay, so I'm just going to, for every item that comes in, along with each regular hash function h, I'm going to have this sign hash function. It's going to give me a random sign along with it. Okay, and so now my algorithm is going to be for I equals 1 to m, for each hash function for r equals 1 to t. I'm going to do the C of r, h of r of ai. It's going to get C of r, h of r, ai, plus the sign of r of ai. Okay, so I'm going to increment or decrement depending on the sign. So if it's positive, if I get positive, I increment the counter. If it's negative, I'm going to decrement the counter. And so this is going to be, this is my update. And so now my query is going to be similar, except I'm not going to use so my estimate now, S of A of a query, which is going to be my F of Q hat, is going to be equal to the median of the set C of R, H of R, Q times sine of R, Q. And this is for R and set T. Okay? So instead of taking the minimum, I'm going to take the median now of the set.
Hello, what's that?
This is the median of a set, right? So I sort them and I take the one that has equal number of things on either side. So I'm adding or subtracting here. So I'm not going to go through the full analysis so I can get to the other stuff again. But this intuition, what's going to happen is what the property I'm going to have is that the expected value of FQ hat is going to be exactly equal to FQ. I'm going to have the right expected value. The reason is because for every other item, the ones which are not Q, I randomly either, whichever ones happen to collide, I randomly either add them or subtract them at random based on these sign hash functions. So my collisions could be positive or negative, so on average they're 0. So the expected error is going to be 0. Well, the expected error is not 0, but the expected effect of any one of them is 0. Now, but there's variance in here, and so the error bound is going to depend on the variance instead. So you take the median now, because if I took the average of them, if I had one really bad one, it's going to pull it off. The median is more stable. In fact, the median is going to be that I'm going to have some probability of having error, and it's only going to be bad if over half of them are going to be bad in the same direction. And so this is how you can use the median. Instead of saying over all of them are bad, I say over half of them are bad. And so you end up doing, so T now ends up being, I think it's going to be something like 2 log of 1 over delta instead, because I had to say half of them are bad in either of the directions. And then K, I think, is again going to be, is now going to be 2 over epsilon squared. So now I'm going to get a worse dependence on epsilon. In fact, this is much worse than before. In fact, there's even going to be some constants in here. There's some constant times 1 over epsilon squared. So I'm going to get this O of 1 over epsilon squared here. But the error bounds, so the error bounds I'm going to get are that f of q minus f of q hat. It could be larger or smaller, is going to be less than epsilon times f2, and f2 is going to be the sum over j in n fj squared square root. Okay, so this is called the second moment of the frequency counts. So instead I had just the sum of these before. That was m, the total count of them. It turns out that this f2 moment is typically much smaller. Yeah, this is typically going to be much smaller than the total count. What's going to happen is, especially if the distribution is skewed, it's going to make it a much smaller. So this turns out to be a much tighter bound than before, but I need a larger size. And these work roughly the same in practice, as it turns out. They work about the same. I mean, that's not too surprising because they look pretty similar, but they work about the same in practice. And if the distribution is very skewed, and as we'll talk about these light and heavy tail distributions later in class, then actually if it has a heavy tail, then this is going to work much better. If all of the mass is in one item, then they're going to work about the same. But if you have a very heavy tail of your distribution, like the words in the English language fall off, their frequency falls off pretty slowly, then this will actually work better in practice, because this F2 bound turns out to be better. Okay, so I'm not going to talk too much more about that, but it's kind of a simple trick on the variation on the count min sketch. Okay, so let's talk about these frequent item set problem for the last part of class. And so and we'll talk about the a priori algorithm. And so why it's called that, I'm not really sure. It's probably written down someplace, but there's some parts of like science where they feel like they need to give some catchy name to every algorithm, and sometimes it's clear where those names come from, sometimes it's not. Okay, so this is frequent item set. So this is going to be different than the frequent item. Instead of getting a stream, and you can still think of this in the streaming sense, but often it's streaming only in that often this data gets to be really big and it will live on the disk of your computer. And you can access it on disk, but you only want to read it a few times. So you're going to do this with multiple passes over the data instead. But so we can think of it as a data set A, where A1, A2, and so forth. AM, but the size is not so important because each of these objects is going to be a bunch of elements. There's going to be a set of elements now. So each of the items in the stream is going to be a set of elements. Let's call this BI1, BI2, BI3, and so forth. Okay, so now each element in the stream is a set, and you should think of this is often called these are often called these market basket data sets. So a common way to see this is if you're going to a grocery store and these are the items on your receipt, right? You don't buy one item at a time, you go and buy a bunch of things at once. You buy milk and bread and all this other stuff. Right? So each item in the stream is now a set, and you want to know which items are typically bought together. So you want to know the frequently occurring sets of items. So it doesn't have to be everything in one particular basket, but a subset of many of the baskets. So people buy milk, eggs, bread, and then their favorite specific brand of cookies. Right? Those cookies may not occur, but the fact that they brought milk and bread together a lot happens to many people. Okay, so the goal is to find and so then we'll say all of these BIJs, each of these occurs from our universe now. So now this is the set of all items in the grocery store, right? So we want to find all subsets of which co-occur more than some phi in more than phi m of the baskets. Okay? So more than a phi fraction of all the baskets are, the alignment's not quite right on here. Okay, good. So more than a phi fraction of all the baskets contain this subset. Okay, so before knew that there could be no more than individual items, but now M is the number of baskets, so you might have a different set of subsets. Kind of the main insight is that, say, milk and eggs occurs, phi m times, then both milk and eggs occurs phi m times. right? So if we see the combination milk and eggs together a lot, then both individually milk and eggs as a single item set must also occur a lot. Occurs at least this much, right? You could have bought eggs without milk, you could have bought milk without eggs, but if that pair occurs a lot together, then each of the individual things must also occur a lot. Okay? So this tells us two things. So one, there may be a lot of these combinations of these subsets occur. We're only going to return the these maximal sets. Okay, this will cut down greatly on the number of sets we have to return. So if eggs and milk both occur with more than phi m frac of the sets, then I don't need to return just eggs or just milk. Okay, so I only return the maximal sets. I still don't necessarily have a bound on the number of these, but it turns out in practice it's always much, much smaller. Okay, so we're only going to return the maximal sets. That's one implication. The other is this tells us how to run this a priori algorithm. Okay, so how this a priori algorithm uses this fact, but instead of it uses the contrapositive of this. So it works in these rounds. Let me just describe the algorithm in rounds. So in round 1, and so the input to it is this value phi, or this total size phi m that we want to find. So in the first round, we're going to find all individual items occurring more than phi m times. Okay, so I'm going to just look for one item at a time. So I'm going to first find, so I'm not going to worry about pairs of items. This is a much bigger search space, right? If there are n items, then there are roughly n squared pairs of items. So I don't want to try and keep track of all these initially. Okay, so I'm going to find all of these, and you know, and I can use something like these other sketches to find them. They don't give quite the right guarantees, even if I set them so that the lower bound is there, because the meaning of m is different here. I need to know the total number of items that occur over all of the receipts, all of the market baskets. So if I set m is equal to, or uppercase m, is equal to the sum over I, or the AI, the size of AI, right? So these were the size of each basket. Then I can run, say, the Misha-Gries algorithm with, or like some version of the heavy hitters algorithm, where I'm using this parameter m as the total size of the domain, and I set, and I only return heavy hitters. So let's say I can return one of these heavy hitters where I use the total size as m. I just kind of chain together these market baskets, and I set the threshold at phi m minus, phi uppercase m minus epsilon m. So then I can kind of use these heavy hitter techniques. Well, just reading over the data once in this first round, find all the things which are individually, just these are large enough. Okay? And so this is going to give me a set of these items. So B1 up to BK. Right? So this is going to be a subset of n. So this is the output of round 1. Okay? So this output of round 1. So then in round 2, I look at all pairs, a set of these sets. So B1, B2, B1, B3, up to BK minus 1, BK. Right, so now I'm going to have all these pairs, but this number of pairs is much less typically than n. Most of the items don't occur that frequently. Right, so I only look at the pairs which I know all the individual things occurred frequently enough. And so now this is typically, so this is usually much smaller than n. It's usually actually much, much smaller than n. Okay, so I put a, if you write two less than signs, this means it's much, much smaller. That's a semi-formal notation. Okay, so so in round 2 I do this, and now again heavy hitters on well, so you what you can actually do is just keep some counters, say for all pairs, or if this number of pairs is very big, you can actually run, you can keep track of each of the individual k, and then run some for the heavy hitters, again with b m minus epsilon m. Okay, but now if it's not one of the items that's in my set that I've kept track of, one of the k items that I found from round 1, I can ignore that completely. I don't need to worry about that one anymore. I only care about things that occurred in both of the pairs. That occurred where I see a market basket, things that occurred, at least anything interesting. The ones that were interesting after the first filter. Okay, and so then, and what happens is then at the end of this, I'm going to get this these set of these heavy pairs, right? So this is going to be a set B1, Bj, right? So, the B1, B2 may not have been big, but B1, Bj, B7 is going to be big, right? So, and now this set of pairs is going to be much smaller. Okay, and now in the third round, I'm going to consider only triples, but so every triple has each of its individual pairs had to be in the set from round 2. Okay, and so there could be n cubed triples, or if there were k sets at the end of round 1, there could have been k cubed triples. But now I only consider the ones that they both must also hold. So then this filters it again. And then you keep doing this, and each round, the set of things you're keeping track of tends to get much smaller and smaller. Typically, the largest set happens at the end of round 1 or maybe round 2, but after that, it usually gets much smaller very quickly. Okay, so I didn't go through this in full detail. This is the main idea. Did you kind of, if you go in the notes, there's kind of an example where you can go through with this small set. Here, let me just show this to you quickly from the notes, so you can see it. Hopefully. All right. Good. So here's my market basket data set. Each of those T1 through T12 is a basket. This is a set of items that I saw. Okay, and so now in this example we go through, I want it to be in at least 1/3 of the basket, so which occurred at least 4 of the baskets. What are the objects which occur more than that? Right. Okay, so in the first pass, here the ones which are in bold occur at least 4 times. So 2 occurs 5 times, 3 occurs 4 times, 6 and 7 occur 8 and 4 times, and 9 occurs 4 times. Right, so I have 5 things left out of 10 after the first round. Okay, so 2, 3, 6, and 7, and 9 survive. So I'm going to get these these pairs, and then I make another pass over the data again, over the pairs 2, 3, 2, 6, and 9 occurs at least 4 times. Now I only have one pair, so I can't have any pairs in each triple to occur that many times, so I can stop. I can return this maximal set, and also kind of the 1 by itself, or 2 by itself, 3 by itself, and 9 by itself. Okay, so kind of a clever algorithm, but that's basically it. There's been a lot of other work kind of using the same idea for counting, for finding cliques in graphs. There's some version that works kind of like this. The trick is to filter stuff very well. Okay, so I'm just going to quickly mention the relation to Bloom filters for 2 minutes to wrap up class. And then I'll do this, and then I can probably I went through some stuff quickly. The difference between the Bloom filter and the count min sketch is that a Bloom filter, it doesn't keep a counter. It just keeps, it's only keeping a single, typically a single hash function. Sometimes you can use two hash functions on the same thing. So it'll keep a single row, a single hash function, each one, and this will go from, or set n to k. But the difference is each of these items, so in here, we'll say this B1, B2, B3, up to BK. So each BI is going to be 0 or 1. It's a bit. And so you get compression by storing, so this is only for storing a set, whether you want to check whether something's in the set or not. And so instead of storing a counter, which has this log n overhead, you only have to store bits in each of these things. Okay? And so then initially, you set all these BIs equal to 0. And so then on the update step, you do, so for all elements in a set, you want to load them into the Bloom filter and so actually you may have a few of these hash functions. So for j equals 1 to k, you set b, you set the bit hash of j of x equals to 1. So if it was already 1, it stays 1. If it was 0 before, it gets. Okay? And so I've hashed multiple hash functions into the same domain. Right? So this hash function might end up here, and this one might go here. So I'm going to set both of these values to 1. Okay, so now I want to ask, is x in the set? And so I say true if and only if for all j in T, that b of hash of j of x is equal to 1. So only if all of the bits are set 1 do I say it's in the set. Okay, so if you just use one hash function, it's not that uncommon to get these collisions. But if you use multiple hash functions, then you need everything not to be in a collision, and so you kind of get to amplify. The analysis of it, there's kind of a sketch of the analysis in the notes, but the actual analysis is actually a fair bit more complicated. and it's a little hard to analyze, but the sketch gives a rough approximation of what's going on here. But you kind of overload multiple hash functions into the same set. So instead of having hash functions hashed separately, you kind of push them all together, and then you put all your bits in the same row. So then k is going to be a little bit bigger, maybe, the same space, but the hash functions will set multiple things to one. Okay, so if you've heard of bloom filter, it's similar to what we talked about, but not exactly the same. It's not keeping counts, it's just keeping whether something is in the set. It is going to have no false negatives, but might have a false positive. Okay, so that's the very quick bloom filter. Great, so we'll start talking about high-dimensional data and regression and stuff on next week, Monday. I'll also talk to you a little bit about the first midterm, which will be a week from Monday next week, and kind of what to expect in there. All the questions should be easier than homework questions and things that you can do without calculation. So don't start panicking about it, but you have to review your materials.